Today we'll be going over section 6.1, confidence intervals for the mean with our standard deviation known. When we work with confidence intervals, we'll be focusing on values that are acceptable highs and lows. So there's going to be a min that's acceptable and a maximum that's acceptable according to some given information that we're trying to compare to. For 6.1, we're going to be working with our average, or x bar, and we're going to try to figure out an x bar that is a probable minimum that will still work and a probable maximum. Now, these values that we come up with will depend upon a confidence interval that we will be being asked to work with. Another thing I want to emphasize before we begin this section is the title. It says that our standard deviation is known. Because we are given sigma, we know we're being asked to work with a population standard deviation. And that's really important. A population standard deviation is slightly different than a sample standard deviation. So this is what makes 6.1 unique. Also, throughout this chapter, I have included this video that shows you step-by-step calculation for each type of problem that you'll see for this chapter. Alright, let's begin with definitions. Estimating population parameters. In this chapter, you will learn an important technique of statistical inference to use sample statistics to estimate the value of an unknown population parameter. In this section and on the next, you will learn how to use sample statistics to make an estimate of the population parameter mu when the population standard deviation sigma is known or unknown, which is our next section. To make such an inference, begin by finding the point estimate. Definition of a point estimate. A point estimate is a single value estimate for a population parameter. The most unbiased point estimate of the population mean is a sample mean x bar. As a result, x bar is an unbiased estimator for mu when the standard error sigma over square root of n of a sample mean is decreased by increasing n. It becomes less variable. So this is saying that x bar is a good estimate of where our mean will be. Because remember, this is a sample, this is a mean. So depending if we're given a population or a sample, they might vary. But the larger our n is, the closer it will be to the mean mu. Because we'll have a bigger group and thus it'll be better suited to estimate a population mean. Let's work with example 1. So each one of these examples is setting us up to find the margin of error. Example 1. A researcher is collecting data about a college athletic conference and its student athletes. A random sample of 40 student athletes is selected and the numbers of hours spent on required athletic activities for 1 week are recorded. Find a point estimate for the population mean, the mean number of hours spent on required athletic activities by all student athletes in the conference. Alright, don't let the wording kind of scare you a bit. We're just being asked for a point estimate, which is your x bar. It's your average, right? So to find our average, it's defined as the sum of our frequencies divided by our number of samples. In other words, add them all up, it adds up to 842, and we were told we had 40 entries. Our answer is about 21.1. Now you don't have to enter each one of these entries and add them up in your calculator. You can always use a list in L1 and do your 1 bar stats like we did back in chapter 2. So we wanted to find the mean. That's what that question asked. Moving forward, The probability that the population mean is exactly 21 is virtually zero, but by using a point estimate, we can estimate an appropriate interval. So we're going to be working with this mean, and we're going to try what works. What is closest to that? We're going to try an interval that works with that. Definition of interval estimate. An interval estimate is an interval or a range of values used to estimate a population parameter. Definition of level of confidence. The level of confidence C is the probability that the interval estimate contains a population parameter, assuming that the estimation process is repeated on a large number of times. This leads us to our central limit theorem. We know from the central limit theorem that when n is greater or equal to 30, the sampling distribution of sample means approximates a normal distribution. The level of confidence C is the area under the standard normal curve between critical points negative ZC and ZC. Critical values are values that separate sample statistics that are probable from sample statistics that are improbable or unusual. So we'll talk about this soon because I know these ZC values are new to us. These critical values are pretty much your Z scores, but they're special Z scores that we'll use in this section. A critical value. You will usually work with 90, 95, and 99 levels of confidence. Here are the Z-scores that correspond to these levels of confidence. So we have a formula above each, along each way, and I'll talk about them relatively soon. When we're being asked to work with a 90% confidence interval, we have a critical value of 1.645. When I have a 95 confidence interval, we have a critical value 1.86, 99, 2.575. So what do these numbers mean? So let's take our bell-shaped curve, right? Let's assume it's very bell-shaped and very symmetric. And we know we have 0, which is our mean, and 0 according to standard deviations. So let's take a look at that first one, that 90%. So this is saying we want to work with a confidence interval of a 90%. So we want to work with only 90% of the values. Well, 90% that holds true, right? So if I only want 90, I need to be able to exclude this chunk that isn't 90. We don't want this. So I need to find that cutoff point. These are these critical values. So where does this 0.05 come to play? Well, we know that our entire bell-shaped curve, the probability is 100%. And if I want to work with 90%, what's left? We have 10%. But we have 10% to split between two tails. So 10 divided by 2, I'm left with 5% and 5%. Okay, now when we work with percents, we must remember that we have to, if we want to work with it in math, we need to change it to decimal form. So we're going to take that decimal point and move it to the left twice. So in decimal form, this is 0.05. And this is where that 0.05 shows up in our chart, along with the other tail, it's 0.05 in decimal form. So this is what it's saying by alpha divided by 2. We're taking that leftover part and dividing it by 2 to account for both tails. And this is the work that we set up for it. 1 minus our alpha times 100 and then we have alpha divided by 2, And then we have our z-value of alpha divided by 2. Again, it's referring to that 0.05. Now again, these z-values represent the z-scores. So we want to make sure, well, we have that chart to guide us, but if you're unsure, you can always find it yourself. So you can ask, go through the process, maybe do im norm of 0.05 along a symmetric curve, and you'll get a z-value according to it. You should get 1.645. Now, because it's symmetric, then this one will also be 1.645. So this is where we get these critical values, these Z's, C's. Moving forward, the difference between the point estimate and the actual parameter value is called the sampling error. When mu is estimated, the sampling error is the difference of x bar minus mu. So our sample mean minus our population mean. Definition of margin of error. Given a level of confidence C, the margin of error E, sometimes also called the maximum error of estimate or error tolerance, is the largest possible distance between the point estimate and the value of the parameter it is estimating. For a population mean mu, where sigma is known, the margin error is E is equal to ZC times sigma over the square root of n. That is the margin of error for mu when our standard deviation for our population is known. And these two conditions must be met. The sample is random, and we must have at least 30, or we must be told that it's about normally distributed. Example 2. Use the sample data in example 1 and find a 95% confidence level to find the margin of error for the mean number of hours spent on required athletic activities by all student athletes in the conference. Assume the population standard deviation is 2.3 hours. All right, so whenever you read a question, I always have to read it about 4 or 5 times. I have to see what the story is telling me, try to see what we're going at, see what's given. It takes time, right? Now our question is asking us to find the margin of error. Okay, well, we just learned a formula to find our margin of error, right? Our margin of error is E is equal to ZC of sigma over square root of n. So we need 3 things. We need ZC, we need sigma, and we need Rn. So we can input them into our formula. All right, ZC is a critical value that comes attached to the confidence interval. Because our confidence interval is 95, I would take a look at my chart. And 95, I have to work with a ZC of 1.96. So I write 1.96. Our sigma, well, that's given, right? It's telling us that we have a population standard deviation of 2.3 hours. So 2.3. And n. Well, recall from example 1, they told us that we had 40 data entries. So our n is 40. All right, let's go ahead and use our formula. So E is equal to 1.96 times 2.3 divided by square root of 40. So I suggest you first do what's in the parentheses. So say take 2.3 divided by square root of 40, get an answer, multiply it by 1.96. You should get something close to 0.7. That is our error. So let me help you build up what we're moving forward to. So I have this mean, and I want to find that probable lowest and maximum value. So we're going to subtract E from our mean, to get our minimum, and we're going to add E to find that maximum. Now we're going to put this together in a chart so that we can keep track of our work. Confidence intervals for population mean. Using a point estimate and a margin of error, you can construct an interval estimate of a population parameter such as mu. This interval estimate is called a confidence interval. Definition for C confidence interval for a population mean mu. A C confidence interval for a population mean mu is x bar minus E less than mu less than x bar plus E. So don't let that notation fool you. It's just what we drew out in our number line, right? We're going to add and subtract that E value. The probability that the confidence interval contains mu is C, assuming that the estimation process is repeated a large number of times. All right, so here are your steps. So if you're in a bind, you can always check out these steps. It puts it all together. So let's go through our guidelines, and you can also find these on page 301 of your book. First, you want to verify that your standard deviation is known. If they don't use that symbol, that sigma, or if they don't use the words population, standard deviation, then we're going to rely on a different method, maybe from a future section. All right, so if we know we have our population standard deviation and that we have a sample of 30 or more, or that's approximately normal, then we're good to go with the following steps. 2, find your x bar, so find your mean. 3, develop the correct critical value for the problem. 4, find the margin of error. Here's your formula. And 5, we're going to add and subtract that from our x bar. Hence, that left endpoint, you're going to subtract E. For a right endpoint, you're going to add E. And if you put everything together, that's our compound inequality. Let's go on with example 3. Use the data in example 1 to construct a 95 confidence interval for the mean number of hours spent on required athletic activities by all student athletes in the contents. All right, so let me draw that image so we get an idea of what we're looking for. So we have an x bar. We want to find a minimum and a maximum. And we do this by subtracting E to that number of x bar, and we do that by adding E to our x bar. So we have set up ourselves to answer this by each problem. From example 1, we found what x bar is, and x bar is 21.1. From example 2, we found the value of E. We found that E is about 0.7. All right, now let's put that together. So let's go ahead and you can use the formula if you'd like. I like the picture. It seems to make more sense to me. So I'm going to draw that picture. So I have that mean, which is 21.1, and I'm going to subtract E, right? So I have 21.1 minus E, which is 0.7, and our answer is 20.4. That's one of our answers. And then we're going to add E to find our max. And so that ends up being our mean, 21.1 plus 0.7. So we add them up and get 21.8, and that's our maximum. It's written as our left endpoint and our right endpoint. So we have our left endpoint and our right endpoint, and we can write them as 20.4 and 21.8. So this would be our final answer. All right, now in this class, though it is a math class, the hardest part and the part that I consider what this class is knowing how to take your information and how to interpret it and how to go about it. So we did everything by hand, but please feel free, and I actually encourage you to use your calculator. That's what we have it for. So our calculator does all of this work for us. If we wish to use our calculator, work, you have a video above that shows you how to use your calculator and it shows you how to use your buttons. But let me outline the steps. You're going to go ahead and press Stat and scroll over to Test. And then you're going to scroll all the way down until you find the value Z, the entry Z interval. And you're going to enter all of these pieces. You're going to enter your X bar, your confidence interval, in this order. So it will lay it out for you. So you have to enter your standard deviation, your X bar, your sample size, and your confidence interval. You have to make sure that it's in decimal form, so 0.95. Otherwise, it might give you an error. Also, make sure on the side, once you get to your screen for Z interval, make sure that stat is highlighted. Stats is highlighted. When you enter data is when you have your raw data, and it'll set you up for a list or information to enter from a list. Now your answer will be given to you just like it is here. So you'll have commas of your minimum value and your maximum value. All right, that's it for this section. I hope you found this helpful. If you have any questions, please feel free to email me or post them in our discussion board.